In the old days, we sequenced genes by hand.
In the 80s, when sequencing DNA, determining base pairs in genes, my project was to sequence a gene.
You ran a gel, you used radiation to be able to see the different tags.
It took me 6 months to determine 700 base pairs.
And you actually counted them by hand and then had to log them in to the computer before you could actually do any kind of analysis on them.
In humans, there's approximately 3 billion base pairs.
It's like trying to put a puzzle together with 25,000 pieces, and you don't even have a picture to go by. You're just figuring it out as you go along.
The beauty of this molecule and the elegance of this molecule was absolutely incredible.
There are only a handful of people, perhaps 10 today, who are members of all 3 national academies in the U.S.
He's remarkably good at actually explaining complex concepts and making people at least think they understand them.
I like to see myself as a kind of cross-disciplinary, multi-dimensional scientist that tries to bring many different things together.
Either you're part of the steamroller or you're part of the road. And I think it's a similar situation for Lee.
I read a book when I was a beginning assistant professor at Caltech called The Structure of Scientific Revolutions. And it's about paradigm changes.
You hate to characterize someone as a steamroller, but there are plenty of forces pushing back against you, and you just got to keep pushing forward.
I decided I'd spend half my time trying to develop new technologies that would let us decipher more effectively biological information.
There are 4 big landmark discoveries. There was the discovery of the structure of DNA. That was Watson and Crick. There was manual sequencing, Sanger sequencing, automated sequencing. That's what Lee was recognized for. And there's the Human Genome Project.
Yeah, Lee's great, I think insight as to where biology was going was that data collection had to be mechanized. You couldn't have postdocs, spending 3 or 4 years determining a DNA sequence. It should be done by, or could be done by a machine.
I would say there are a number of things that got me started in the field of genetics. One was a father who was an electrical engineer and brought naturally an interest in engineering to me. The second was a brother who had Down syndrome. It really made me think about genetics for the first time in my life. My senior year, my chemistry teacher asked if I'd help teach freshman biology. And I said I would if I could teach using Scientific American. And one of the courses that I taught was a course on the structure of DNA.
Genes are made up of DNA, and DNA in turn is made up of these molecules called nucleotides.
Genetic material is made up of 4 units called AGTC.
Being able to sequence a gene is the first step in understanding the function of a gene. Once you understand that there's a disease or a mutation or a problem, what you need to find is where does that occur.
Say we have an A where we should have a G, then potentially we can target this specific mutation in order to diagnose the disease.
What Lee saw with incredible clarity was this virtuous cycle in which the needs of biology drive the invention of technology, which changes the biology you can do, which changes the technology.
And he was a young professor at Caltech, and very much at the mercy of the senior professors. And they told him that this working on technology was not something he should be doing. He should focus on the biological problems. And he chose rather courageously to ignore that.
So to invent the DNA sequencer, we had to bring together a chemist, an engineer, a computer scientist, and myself, a biologist, a molecular biologist. And once we got that critical mass of people together, we conceived how to do it in a very short period of time, less than 6 weeks.
It really speeds up everything you can do. And of course, at the same time, it also allowed for the sequencing of entire genomes.
The impact on society that will improve the human condition and has improved the human condition is a large number of drugs that have been developed due to what we've discovered by sequencing the human genome.
When you look at the huge strides that we've made over the last decade or two, just being able to use automated sequencing and what that has led to, the complete renovation of molecular research and DNA discovery.
In addition, it has brought a huge amount of accuracy to the discipline of forensic science.
The work that I do on plants really will help impact food and food security for our country and for the world. It will also impact sustainable fuel, green fuels, to be able to look at plants and to be able to figure out what they make and what they make that we use as human products, and to be able to modify those. So it's not just the medicine, it's also everything else you use every single day.
There was a large conference, I'm not sure which one, but Dr. Hood was giving the plenary lecture. There was probably 1,000 people in the audience.
When he actually invented the sequencer, it was a prototype and was not suitable for being a machine that was in everyone's lab, and so he had to take it out and commercialize it.
What he was talking about was new technology for this DNA sequencing, which was just in its rudimentary stages in the early 80s.
He went to more than a dozen instrument companies trying to get them to commercialize it, and nobody was interested. And that's what caused him to found ABI, Applied Biosystems. It wasn't that he wanted to be an entrepreneur, it was that this instrument needed to be replicated.
In the end, we developed a series of 5 different machines that really let us decipher DNA, RNA, and proteins in various ways.
Years ago, I knew that he and his wife met in a high school debate tournament in Montana. And I asked Valerie, Lee's wife, who had won the debate. And they were on opposing teams. And Valerie said, "One of the great things about my husband is he doesn't recognize defeat even when it's staring him in the face." It was Bill Gates who recruited him to the University of Washington in the first place by endowing Lee's position and causing the new Department of Molecular Biotechnology to be created.
They enlisted me to meet with Lee and encourage him, as well as provide some of the resources that would allow Lee to exercise his great innovation.
So what really motivates me is how you achieve these paradigm changes, how they become accepted.
Lee was in the very first meetings about sequencing the human genome.
In the beginning, everyone is against your paradigm change.
I was among those, quite skeptical, moving forward until at a meeting where Lee was there and all the proponents were there, with most of the audience unsympathetic.
Only trivial scientists would want to carry out such routine tasks.
So it was the coming together of 2 groups, biologists, geneticists who wanted to understand disease, and the people who just loved technology and wanted to make it go faster. But even the skeptics, at the end of it, realized if we could do it, we got to do it.
It's so exciting to see when the paradigm change unfolds, how it revolutionizes that aspect of science. It's utterly clear that for paradigm changes, you need to create new organizational structures to really achieve them.
Lee has more lives than a cat, right? He's had all these phases to his career as a chemist, as a biologist, as a doctor, as an inventor, an entrepreneur. He just keeps moving along with this enormous vision.
He's created an Institute for Systems Analysis that is
more world-changing. It's what he calls systems biology at the Institute for Systems Biology. There are now 200 top scientists over there driving things forward.
And we're looking at a large number of different disease types: Parkinson's disease, Alzheimer's, Huntington's, and a number of others.
I'm a big believer in the great work Lee is driving at the Institute for Systems Biology. The quality of the people there, the way they're looking at some of the tough challenges and building tools. Lee's always understood that the tools advance the science.
What I'm attempting to do now is create a revolution in medicine.
P4 medicine.
P4 medicine.
I can never remember all of the P's.
Dr. Hood has an entire set of P's.
It's personal, participatory, predictive, and some other P.
The 4 P's, including personalized, preventive, participatory, and predictive medicine.
Gene sequencing is becoming so inexpensive. It's literally headed towards $1,000 and soon $100, that each of us is going to have our genome sequenced
We could take each person and determine if that person has mutations in genes, changes that may make them susceptible to a certain type of cancer, diabetic disorder, growth disorder.
With individuals having their own genome sequenced, then therapies and medicines can be designed and manufactured based on their personal needs.
I forecast a whole new wellness industry will occur that in time will far surpass the disease industry, the healthcare industry of today.
Dr. Hood was awarded the Russ Prize in recognition of the impact that his invention has had on society. In addition, the impact that it will have in the future.
One of the university's greatest sources of pride is the Russ Prize, a vision Fritz and Dolores had decades ago.
Fritz and Dolores were great friends of engineering. They believed that engineers really were the future of the world, really.
There's been very, very incredibly prestigious individuals who received this prize, of which Dr. Hood is one.
A lot of the innovation in the gene sequencer was in fact chemistry. There was very fundamental chemistry that had to be achieved, a huge amount of engineering.
I think having the Academy of Engineering recognize that, it's significant to all of us because of the convergence of engineering and biology in the modern century.
Dr. Hood's work has not just affected the research, but it's also affected education.
By involving both undergraduate students and certainly graduate students in my work allows me to help train the next generation of biomedical scientists and engineers.
We have students working in the genomics facility, students working in my lab and other labs across campus.
All in the context of this molecule called growth hormone, which makes us grow.
Learning these techniques as if they're common everyday things.
Find those molecules that serve as the best targets for stopping cancer metastasis.
We can only dream about where those students will take these techniques as well and what it will benefit for them.
It's a real statement that the Russ Prize has been awarded to Lee for this work. It's really his entire career has been understanding this virtuous cycle of technology and biology pushing each other forward and enabling discovery and really making each field much richer than it would otherwise be.
I think it means that you've really done something that's made a difference, that you've caused a paradigm change.